Okay, so molecular substances. That's the same one we just had on here. So molecular substances are made up of more than one nonmetal, all right, joined by what we call a covalent bond, and I'll explain to you why we call it covalent in a moment. Examples are, obviously, simple molecules like H2, two atoms bonded together, slightly more complex molecules like water, and fairly large biological molecules. They can be huge, in actual fact. Like a DNA strand itself is one molecule, all right? And it's got thousands and thousands and thousands of atoms in there, but it's still one molecule, all bonded together with these covalent bonds. So molecules can be big, and they can be very small, but in the end, they're all bonded together. They're not just kind of attracted to each other like ionic compounds are. They're literally bonded together with these bonds. Okay, so I do want you to write what's in the box. You do not need to write the rest of it. Now this is a term that I've used already in this lesson, and I've used before. But technically, it is only associated with molecular substances. And that's the term molecule. So the smallest part of a molecular substance that has the properties of that substance is called a molecule. So if you had one water molecule, it would be a molecule. But as soon as you break this down further, you don't have molecules anymore. If you break the bonds in a water molecule, you've now broken it down to a substructure we call atoms, right? So that smallest chunk that has the properties of the thing are called molecules. So a sugar is a molecular substance. A bag of sugar contains a bunch of sugar or sucrose molecules, all right? An ionic compound technically does not contain molecules. It contains a bunch of ions. We actually call that smallest piece that we write down in a chemical formula, we call that smallest chunk a formula unit, the smallest unit which makes up the formula. But in the end, we can't really state where the formula unit begins and ends because we could pick any pair and that would be a formula unit. So this is not as distinct, where here we've got one distinct particle, a molecule. All right. How do nonmetal atoms bond? So you can write that down. When two nonmetal atoms bond, they cannot gain the other's electrons because they're both gainers, right? Remember, nonmetals are gainers. They're going to gain to fill their outer shell. They're not going to gain because it's easier. They're not going to gain because it makes them happy. They gain because they have a really strong pull on electrons. Instead, nonmetal atoms share their unpaired electrons to fill their outer orbit. And we call this shared pair of electrons a covalent bond. Again, I'll talk about where the term covalent comes from once we start drawing some of these structures. Again, let me remind you, electrons are attracted to the nucleus, and some electrons are attracted more forcefully than others. Nonmetals attract electrons with great force. Metals do not attract their electrons with great force. You put a metal up against a nonmetal, really it's a tug of war, really what it is. You can think of it like, I don't know, I was going to say Pokemon. My son plays with Pokemon. What the heck is his name? Plays a video game thing. Anyway. So Pokemon isn't what I want to talk about. Something where there's a battle for something, but they got to be pulling on something. There's got to be like a tug of war battle. So Pokemon's no good because I don't know what they do. They have powers or something like that. Anyway, I digress. Forget about Pokemon. Two little tug of war people. Don't even know what that is. So metals are terrible at tug of war. They really don't care. They don't really want to play the game at all. But they're terrible at it. They have a very weak pull on their electrons. Non-metals are awesome. They're like the muscle-bound, strong men of the periodic table, or strong women. I'm not trying to be sexist here. Anyway, so you put a metal up against a non-metal, and the non-metal wins the tug of war. Pulls on the electron. It was no contest. Becomes a negative ion. The other one becomes a positive ion. And then they're friends because they hang out in an ionic structure and they kind of stick together. All right, that's an ionic compound. You put two non-metals up against each other, and they're going to pull on the other atoms, electrons, and they're going to hang tightly onto their own electrons. So it's a tug of war that nobody really wins. So what happens is that the only way that they can pull on the neighbors, yet keep its own, is to kind of snuggle up against each other, beside each other, not letting go of each other, right? So, and then that means that you've got this clump of atoms that are hanging on to each other. I've got a really dumb analogy. I came up with it a couple years ago. It's really stupid, but it's the only one I can think of right now. If you're babysitting a little kid, like maybe he's like 4 years old or so, and you come up behind and you go, "Hey, I got your nose," right? You've ever seen that before? See, I got your nose, and then they freak out because they really think you've got their nose. No, you know what I'm talking about? You ever heard that before? It's kind of a silly thing. Let's imagine that one of the atoms literally grabs the nose of the other atom, not just playing the game for fun, but literally hangs onto it. It's kind of silly. And you can imagine that their nose is an electron. So in other words, that other atom wants that other thing's nose. And because the nose is attached to that, the other atom's not going to give it up. So let's just say then that the other atom says, "Oh yeah," or which says, "Oh yeah," because it would sound like that if they had grabbed their nose. And he grabs the other guy's nose. So you've got two people grabbing onto each other's noses. It's kind of an awkward looking thing. And nobody lets go because they have this incredible drive for the other one's electrons, yet the other one is also pulling on the other atom's electrons. That's essentially what a covalent bond is. So what's the only way that they can get around is walking beside each other like this. "Oh, ow, oh, that hurts," that type of thing, going on and on and on. It's silly. It's absolutely the silliest kind of analogy I've ever thought of. I don't even know why I thought of it. But that's kind of what a covalent bond is. I'm not going to let go of my electron, and yet I'm going to also hang on to your electron. The same is happening in reciprocal, in the opposite, and therefore they must kind of hang around together because they're literally hanging on to each other's electrons and they're not letting go. Why? Because they're good at the tug of war. They're not letting go. All right? So when we say they share electrons, I don't know, a hippie must have thought of that term. In reality, it's a tug of war, but the electrons reside in between the atoms. So we can say that the atoms are both using the electrons, and we can flower it up by saying there's some sharing going on there or something like that. But it really isn't. So types of covalent bond. First type I want to talk about is the single covalent bond. And again, just put EG. Wherever you see examples, please just put EG. And I'm going to put two hydrogen atoms together, and I'm going to describe its structure. Now, you can put underneath here Lewis symbols. You might want to put here Lewis symbols of the atoms. And when we put the atoms together into a molecule, we call it a Lewis structure. I often call it a Lewis diagram, all right? So you might hear me say Lewis diagram, draw the Lewis diagram. I mean the Lewis structure, they mean the same thing. And this is of the molecule. Now for the other examples that I have on here, it says the same thing, Lewis diagram, Lewis structure. Don't write that down again. I think we get the idea. The atoms are Lewis symbols, and then the molecule is a Lewis structure. But it doesn't matter. I often lump them together as Lewis diagrams. So, 1H atom, hydrogen. I'm going to put another hydrogen atom beside it. So this time, instead of putting the dot above, I'm going to put the dot beside it. second H atom. To differentiate between one atom's electron and the other atom's electron, I'm going to represent with this with a little X. And they're going to get together. Perfect. They're going to share. No, there's a tug of war, but we can say they're sharing. So these are going to come together here. I'm not even going to put a plus. I'll just put an arrow here. And in the end, you've got one dot from one X from the other, and you have H. Now, this is sometimes called the electron dot diagram because it's got dots in it. A better way to draw this, and this is the Lewis structure, H with a line H. Okay? And this line, whenever you see a single line between atoms, it is then a single covalent bond, and there are two electrons in there. Okay? All right? So if I'm asking you to describe to me how to draw that, you'd say H single bond H. And as soon as you say single bond, I know to draw a line because we are all fluent in the words of chemistry. So when you say single bond, I think of a line, and you should too. Okay? And you should also think that there are two electrons in there. Now, usually when we draw a Lewis structure, we want to see whether the atoms are happy. We know that they don't actually get happy. But are they happy because they've got their full outer shell? Because in the end, that's what they want, right? Hydrogen's a special case. How many electrons does hydrogen need to be happy? It just needs 2, where the other guys need 8, right? So hydrogen just needs 2. And the way you check for happiness is to ignore the other atoms. Look at that hydrogen there. It's got 2 around it, doesn't it? Even though one of it came from the other atom, it doesn't matter. It's got 2. That makes the first hydrogen happy. The second hydrogen is happy as well, because it gets to share the other electron. I look at it this way as well. 2, 2, everybody's happy. The hydrogens are happy. That is a good Lewis structure. That's how we tell whether we've done it properly, okay? I also mentioned to you when drawing Lewis structures for ionic compounds, I think I mentioned it to you, you can't just add dots out of nowhere. The amount of electrons that you start with must be exactly the same as the amount of electrons that are in the final structure. In other words, you can't just add some dots because you think it might look good. You know, this isn't art. It's like you can't say, oh, you know what? That needs a few more dots. That'll look better with dots. You can't just add dots, you know, for the sake of it. How many electrons did we start with at the beginning? 1 in each, but in total, for both of my atoms, there's 2. In the end, how many electrons are in my structure? 2. There's 2 in that bond. So I started with 2 electrons. I have 2 electrons in the end. I haven't cheated by adding extra electrons. You can't have electrons just appear out of nowhere. They've got to be first in the original atom, and they must appear in our final structure. Okay? All right. So that's a single covalent bond, quite easy. Some students, in the end, when I get you in grade 12, I want you to be able to look at H2. By the way, this molecule would be H2. I want you to be able to look at H2, and I want you to think this right away. Boom. Oh, there's 1 electron in each. Boom. I can think that. For students who are new and they start out, I always suggest write out your atoms. And what you can do is, maybe with a pen or a different colored pencil, put a loop around those to indicate that they're going to share, right? They're going to come together, and they're going to come together like this. But ultimately, we want you to go from here over to here. And I don't think that's too big of a stretch, right? You put a loop around that pair, and that makes our pair. Let's do a few more structures. All right. So don't write down Lewis symbol, Lewis structure. We're going to put an O with 2 H's. And again, don't write down Lewis symbol, Lewis structure. You get that. So start drawing your atoms with their electrons around it. And you know what? It really doesn't matter what order you draw them in. You can draw the O and then the 2 H's off to the side. Ideally, hopefully, you're starting to think about putting electrons together any electron that isn't paired up is going to be looking for a pair from another atom. So when I do this, if I'm doing this in order and I start drawing my O, which it sucks because that's not drawing anything, O, and then I do my 1, 2, now I got to draw 6, but I'm going to put my H's over here. So I'm going to put my lone ones over here so I can overlap them there. But you could put the lone ones on that side. It just means you're going to have to draw some big funny loops. But I'm going to put that there and that there because I know I want it to do some overlapping. Electrons love to be in pairs. They're all paired up. They're all paired up. I've got a hydrogen that has 1. And you know what? Let's draw it all as dots this time. Let's not worry about the X's because I'm not going to bring them together like I did that other picture. I'm going to go right from the loops all the way to the other picture. And I'm going to put the other one down here. And now I just have to, it's like playing with Lego. I got to put this together so that everything's paired up, so that electrons are in pairs, and everything's happy. So there's a single, and there's a single. So I can see them getting together and doing some sharing. Okay, tug of war, but whatever, sharing if you're a hippie, tug of war if you are violent deep down, maybe, in some way, I don't know. Competitive, we'll go with competitive. Competitive. All right, and I can see a loop here, and everywhere where you've put a loop, swap in a line, and you've got the Lewis structure or the Lewis diagram. Oh, I didn't want to do pink. 1, 2, 3, 4, line H, line H. Could you have a line on the opposite side and 2 dots on the bottom? Yes, you could. In reality, when you take my grade 12 and I teach you how you predict the 3-dimensional shapes of these molecules, it's actually a bent molecule. So I draw it like that because I know it's bent, because I know I've taken the classes up ahead, right? If you draw it as going across with 2 and 2, it's fine. I'm not worried about that for you guys. We'll train you up later on. 2 single covalent bonds. Is everything happy? How many electrons are around that hydrogen? 2. That's happy. Hydrogen is good. How many electrons around that one? 2. How many electrons around the oxygen? 8. And that's what oxygen needs to be happy. That's a good Lewis structure. We haven't gained or lost any electrons. They're all accounted for in our structure. Because notice we started with 1, 2, 3, 4, 5, 6, 7, 8 electrons. And there's 1, 2, 3, 4, 5, 6, 7, 8 electrons in that structure. Awesome. Yep. 2 of them? Yes. Those are 2 separate single covalent bonds. I'm going to show you one in a moment. But that's not a double. Those are 2 separate single covalent bonds. So if you were to tell me how to draw that, you'd say H, single bond O, single bond H. All right? And then you'd say there are also 2 lone pairs on the oxygen atom. And that would describe to me exactly what that structure is. So these are called lone pairs because they're not being shared. They're all alone. They're lone pairs. Okay? All right, let's do some more. Double covalent bond. Again, e.g., put 2 O's, and don't write Lewis symbol, Lewis structure. You get the idea of that already. So I'm hoping some of us here are already starting to think, oh, we just drew an oxygen, it had 6, and it had 2 of them alone, and the other oxygen, oh, it's got 2 alone as well. I'm hoping you're starting to, oh, and this is going to be a double covalent bond. Whoa, this is exciting. That's exactly what you need to be thinking. So I'm going to draw the O, and again, I'm knowing I want to make connections with another O, and I'm going to put the other O over here. So I'm going to put the lone ones out here because they don't bond. They're already paired up, so they're not going to do it. We'll put one down here. We'll put one down here. O, 1, 2, 3, 4, 1 here, 1 here. And again, I'm hoping you can see some overlap here. This guy is going to get together with this guy. This guy is going to get together with this guy. Now what that means is I now have to have 2 lines in between my O's. And so we draw it like this. O, double bond O, 1, 2, 3, 4, 1, 2, 3, 4. Ooh, ah. Not too stressful? This is, as it states there, called a double covalent bond. And how many electrons are in that little symbol with the two lines? There's 4 electrons in that symbol. 4 electrons in there. Oh, I never did tell you why it's called covalent. What's a valence or a valence electron? What's a valence electron? We've used this term. It's the outer electrons, right? So it's the electrons in the outer shell. When you snuggle up 2 atoms to share those electrons, these electrons that are being shared are considered to exist in both outer shells. So just like you can have co-prime ministers, like in our school, right, which means they kind of share the prime minister's job, right? They're side by side, they're equal prime ministers. We have now covalent electrons, electrons that are existing in the valence shell of both atoms. And so because they're covalent, they're both in both outer shells, we call them covalent bonds. All right, it means that they're existing in both outer shells. That's why we can say that they're all happy, right? Because we can consider them to be belonging to both atoms. Let's check for happiness here. How many electrons are surrounding that oxygen? 8? 8. How many electrons did we start with in total? 2, 4, 6, 8, 10, 12. Do we have 12 electrons in total? 6 and 6, right? How many electrons are in my final structure? How many? 12. So that's a good structure. Everybody's happy, and we didn't lose or gain any electrons. We had a 16 out there at one point in time. I think we even had an 8. It was good. That was fun. A little bit of struggling with some simple math. Didn't think that was going to happen with you guys, but there you go. What's that? That's okay. That's all right. Triple covalent bond. Again, don't write Lewis structure, Lewis symbol. Again, if you're starting to get the handle of it, hopefully you've got pencils out and you're starting to put some dots around. We're going to bring these things together, and it's a triple covalent bond, so that's a little bit of a hint on what's going to have to, happen here. You guys are pretty good at seeing trends in things. How many dots around that N? How many valence electrons? 5. I'm going to put the pair out here. If you didn't do that, it's not a problem. Your loops are going to loop around kind of goofy, right? You're going to have great big loops going all over the place. I've done this a few times, so I know the most efficient way to do it is like this. And you know what? Again, in the end, I'm hoping that you don't have to actually draw the loops, right? Now, I know on some of our sheets that we practice, and there's going to be one tomorrow that you're going to do to hand in, right? I'm going to evaluate it on you. It'll say, draw the loops to show the electrons getting together. And that's a type of a grade 10 thing, which is good. But in the end, when you get to grade 11 and grade 12, I want you to be able to look at a couple of nitrogens and think, oh yeah, okay, and draw the Lewis structure, bam, just in one shot. Just like we do the crossover in our heads, right? Sometimes we're getting so good, we cross it over, we just write it down, we divide off the common factor, we write down the formula. That's awesome. But make sure you read on some of the evaluations. If it wants you to put the nice little loops, then put it in. I hope we got there already. I'm going to put the loops now just to make it look good, make it official. Loop, loop, loop. If you had this down and I hadn't written it down yet, how would you explain to me how to draw this? Somebody explain to me in words what I would do to draw it. So let's imagine I can't see the screen there that has the answer right on it. So I'll face this way. Somebody tell me, how would I draw that? What are you going to say? What do you think? All right, Marissa, what do you got?
So I'm N.
N, or you could say nitrogen, because I know my symbols pretty well.
And then like a lone two.
A lone pair?
And then a triple. Another nitrogen.
Is it the same as that? Perfect. Then you've explained it perfectly. You've got all of the Lewis diagram described perfectly. Nice. Let's define this up. Triple covalent bond. How many electrons in that symbol? Yep, 6. Excellent. 6 electrons. Checking for happiness. Yep, happiness. Actually, there's a name for happiness. I might as well tell it to you. In chemistry, we call it the octet rule. The octet rule states that atoms will form enough covalent bonds so that they have 8 electrons in their outer shell, with the exception of, what's the exception? Hydrogen. So when I say, is it happy, there is a technical term for it. We say, is it satisfied the octet rule? Again, that's a term you don't need to worry about, but that's in the future. So, yes, happy, happy. Did we lose or gain any electrons? No, what do we have? We had 10, 2, 4, 6, 8, 10. Good structure. Okay? All right. Let's now change it up a little bit. And then for the rest of the class, I have a worksheet that has, various combination of atoms that we want you to draw up Lewis structures for. And if you don't have the sheet, I did turn it into a Google Doc, so you could access it on your device. I'll put it up on the screen as well if you just want to do it on a piece of paper. That's a valid move. Tomorrow, I'm going to give you a sheet that you're going to hand in, right? That's going to have questions about drawing these diagrams. And in the past, we've used molecular model sets to make them, but I've found a really neat online virtual molecular model set, which allows you to build the molecules that way. So I'm going to have you work with a partner for a while to see if you can build some of these molecules that you're going to be drawing tomorrow. All right. Don't forget, tomorrow we also have the ionic naming quiz. I'm going to start with that. Okay, it's got 10 formulas, 10 names, right, from our ionic naming stuff. Right. Okay. So, you know what? I'm going to ask someone to just tell me how to draw the Lewis structure. All right, if you think you've got it there. Marissa thinks she does, but I'm going to, yeah. Yes, by all means, you always get a periodic table from here on in any chemistry stuff. The only thing I didn't give you it for was when we were memorizing the names and symbols, but other than that, you get to use it. Yes, yep. No, this is not on the quiz. This is new stuff. I'm only doing ionic naming and formulas. We good to go? So, could somebody tell me 2 C's and 2 H's, what you ended up with to make everybody happy? All right? And if you're not sure, don't worry about it. Get them all out there, see what you can do. But I want to see if we could maybe come up with what this is. So you can tell me the atom, you tell me whether it's a single, double, or triple bond, and tell me if any lone pairs need to go anywhere. Okay? Any suggestions? Anyone? Marissa does, but she answered the last one. You got it? Got something? You got nothing? Have you got the atoms?
Yeah.
Well, yeah, that's looking not bad. You can start putting some loops around.
Is that right? Or no?
That's looking pretty good. Yeah, that's looking pretty good. Yeah, that's looking really good. Yep. Okay, what do we got? Somebody tell me. Anyone? All right, Marissa, what do you got? No lone pairs, right? I like it. That's a great structure. Okay, let's show you where it comes from. Carbon, carbon, 1, 2, 3, 4, 1, 2, 3, 4. Now, you know what? Where you put the hydrogens, it doesn't matter. I saw some people put the hydrogens down here, put the dot here, and here, put the dot there. That's awesome. There's nothing wrong with that. So now you got to pair things up. Just because they're located on the back side doesn't really have any meaning, because this really isn't the way this actually happens, by the way. This is a simplistic representation of how the bonds are formed. How do we know? We just know. Anyway, so I'm not concerned about the positioning of things. So if you're going to do this type of thing, awesome, excellent. And now the only thing that you can attach together are those carbons. Then you're going to do this, you might do this, and then you might do something like this. Whoa, that's a little kind of ugly, but it can turn and bend and twist around. And then that gives you 1 bond, 2 bonds, 3 bonds between the carbons, 1, 1, and that's excellent. Some of you I noticed had the H's coming down. Again, because I know my grade 12 in my university chemistry, I know that this molecule is actually a linear molecule. It isn't bent. This one is a linear one. You'll learn how to figure that out in your future. Yes? Yes, you cannot, that's a great question. You cannot have a quadruple covalent bond, because you might think you could put 2 C's together and make that happen, right? Okay, I got something to show you on that one. This is a good question as opposed to, how do you know, right? Anyway, so let's imagine, actually we don't have to imagine. Let me take these off. These are hydrogens. And this is from an actual model set. So this is carbon, and this is the actual positioning of the electrons. Like I said, they're out like a tripod. They're not flat on a board. So this is really a simplistic representation. And let's then take these bonds off of this carbon. So now this carbon has 4 openings for these electrons. So I could make a bond there, 1. I can make a bond here. Now these are not the double and triple bond bonds, they're longer, but I can actually get it to bend around there and make the bond. I can also get the other one to bend in this way. This is terrible because it's breaking apart. But in the end, I'm going to have 1 bond, all right? In the end, I'm going to have it positioned like this. And then this bond's got to come all the way around back here. And when you try to make that happen, it breaks the other bonds. The structure flies apart. So you can't actually make these electrons sticking out the back come around this way, because it breaks open another bond. So there is no quadruple bond. Okay? There's only triple bonds. All right. So activity, building molecules from molecular substances. Actually, we're doing the question sheet. So if I go to the internet at this point, this is the question sheet. Again, I recently just turned it into a Google Docs, and we're asking you to put together a chlorine and a hydrogen and a chlorine, and a selenium and 2 hydrogens, and a nitrogen and 3 hydrogens. Here's the initial Lewis symbols showing overlap with unpaired electrons. Those are our nice little loops. And then the Lewis symbols of the molecules, okay? So if you have the sheet, great, you're just doing it. If you're needing a device, you can. Those 3 don't log me in, and these need to be logged in on the external network, but they will work. Yes? Yeah, I do want you to show them, because on a quiz or a test, I'm going to make you do it because that's the way they're written, right? But like I said, in the end, I want you eventually to grow up to be good adult chemists so that you don't need to draw all those loops. But for now, show them to me, okay? I'm going to stop my recording here for a minute, and then I'll